Good morning and welcome back to the final date of our workshop on P4 programmable data plane switches. Today, Friday, we will finalize the workshop with two more topics, and after that we will have two lab exercises to reinforce those two topics. So we will talk about registers and packet digests. Registers are stateful objects. I would say the most powerful stateful objects to store information in the data plane. And the packet digest is a mechanism to communicate from the data plane to the control plane. So these two exercises will show us examples on how to use registers and packet digests. Few updates before we start. The recordings up to day number 3 are here. Day 3, 2, and 1 will be posting anytime soon. As soon as we get the recordings, we will be posting day 4, and hopefully by the end of the day will be also day 5. I'm trying to remember if there's any other update. I think that's the only update. Also, the slides of yesterday are already online. So the slides of Dr. Marian Kiran, and also the slides for today. So let's start our program. I will go over registers and packet digests. I will go through these slides, and then we will start the hands-on exercise. And I remember one more thing before we start. The virtual machine for the lab series, the one that we're covering now, is available here. So if you want to download the virtual machine that we're using, here you have the link. The virtual machine for the first lab library is also here, is the first link. And you can download the lab manuals from the cyber training website. For example, here we have the lab manuals for the library that we're covering right now. It's right here. And the lab manuals for the previous library, the Intro to P4, are here. So I will share these URLs in the chat window before we start. So the cyber training website, including all lab manuals, and our workshop website, as always, is here. Right there is in the chat window, that information. Paul, the day 4 workshop videos are available at Western Academy. Thank you for letting me know. So we will be also posting here soon. Thank you, Paul. All right, so let's start with our program today. I will go over these slides. And then we will do the hands-on exercises. So these two topics are, in my opinion, quite interesting. Registers, because they are very simple to use, and we can store arbitrary information in the data plane. And then the packet digest, because it allows us to communicate from the data plane to the control plane and do certain operations in the control plane, and then back to the data plane if that's what we want. So regarding registers, they are stateful memories whose values can be read and written can be read and written in action in the data plane. So that's why they are powerful. We can read, we can write. So they can also be read and written from the control plane. So again, that's why they are so powerful. We can manipulate from both the data plane and control plane. So they are more general than counters. If you remember, counters are associated to tables. In the case of register, we can freely use with tables or without tables. Registers are global memories, and they are managed by the compiler because they depend on the platform we are using. So for the V1 model, here is the definition of the register. If we want to...
Excuse me, Dr. Jorge, I think you're not sharing the slides.
Oh, I apologize. Thank you for letting me know. Let me try again. Is that better?
Yeah.
Yes.
So what we said is, I was talking about registers, and they are very powerful because they can be read and written from the control plane and also from the data plane. Now, how to use registers? Here is the definition of the register, and this is from the v1 model.p4. This is the architecture we are using. First, if we want to instantiate, we want to use a register. There is an instantiation here, and there is a parameter that is given, and this is the number of elements. So you can think about the register as an array, and we have to indicate how many elements this array will have. There is a method to read, and it has two parameters. The first one is the result. So receive an output parameter, where to store the register value. We're reading, we're extracting from the register. So we're placing here what we read, and then the index. And this is which element in this array we want to read. And then we have the write. We are giving the index where we want to write. And here is the value that we're storing in the register. So just three methods, and that's enough. So it's pretty straightforward to use. In this case, in this example, we are instantiating a single element register. So this one here is one element. This is the name R1. And n could be 32, 16, 48. So the value we want. The way to read the register. So first we get the index, to write the index. We want to write in position 0 or element 0. And this is the value that we want to store in the register. And read again. I think I repeated myself. This is how to read. Read from element 0. And we are getting this, or we're storing what we're reading in the variable rest. Okay, here is an example of how to use, and this, I believe this example is further developed in, which lab is this, Eli and Jose? I think it's lab 10 or 8 or 10.
Lab 10.
Lab 10. Okay, so there is an extended example. This is just a snapshot of the way to use register, but if you want to see in further details, you have lab 10. We will not cover lab 10 in this tutorial. The example is how to compute the time between two consecutive packets of a flow. So a flow is a set of packets from sender to the destination, from one sender to that destination. So that's a flow. Typically, we identify a flow as a 5-tuple. But let's say that we want to know what is the time between consecutive packets. On the left-hand side, we have the code. On the right-hand side, standard metadata. And we will use one element in the standard metadata to solve this problem. First, we declare the register, we instantiate. And this register has 16,384 elements. It's just a number. It could be, if there is less than 16K flows, if we expect less flows, we will have a smaller register. And this is 48-bit register. And the reason why is 48-bit, because we will store here what is the last packet or the time we observe the last packet from a given flow. And we will use timestamps of 48-bit wide. So that's why we are declaring this as 48-bit register. We can use registers inside control, inside an action. We are creating an action that will compute the inter-packet gap, the time between consecutive packets. We will return this value, the gap, time gap, in this interval parameter. And we are receiving this flow ID. What is the flow we're computing the inter-packet gap for? We have a variable, temporary variable, last packet timestamp. And here is where we are reading the value of the register. We will store whatever it is in this register into this temporary variable, last packet timestamp. And this is the index. And the register is being indexed by the flow ID. So we want the information from this flow. So we use this flow ID. Calculate the time interval. So the interval will be the current time, the time this packet was observed, the current packet, minus the time of the last packet. And this will be the value that will be returned because this is an output parameter. And then finally, we update the register because the register is storing the last timestamp. So for this flow ID, we are updating the last time a packet from this flow was observed. So it's, I believe, self-explanatory, this code. And you can see in much more detail, again, in lab number 10. So that's one example of how to use register. In our lab number 9, we will use register for a different purpose. We will write a program that uses registers to store the last observed source IP address. And that's what we have here. We have a P4 switch, regular switch, 4 host. And we will program this switch so that we will store in a register the last observed source IP address that is crossing this switch. So that will be our task. Now, the second topic that we will develop today is packet digest. And before describing what packet digest is, I should mention the purpose. So the scenario is as follows. So we have the data plane here at the bottom and the control plane at the top. And the problem is how to communicate, how to send information from the data plane to the control plane. So from the bottom to the top. And there are 2 ways that these switches enable the programmer to communicate this information. One is through a CPU port. Switches have a specific port that is called CPU port that allows the data plane to forward a packet to the control plane through this port. And this is also called packet in, packet out. Packet in, packet out is in both directions. And the second way to communicate information from the data plane is through this packet digest mechanism. When to use this packet digest? Well, one solution is always just to send the entire packet to the control plane using the CPU port. This is similar to a regular physical port, but instead of communicating to another device, is communicating to the control plane. So one solution is always to just forward to the control plane the entire packet or packets. However, if the information is small, the information that we want to send to the control plane is small, we can use digest. So if we want to send, for example, just certain header field rather than the whole header, we might want to use the digest. And based on that information, the control plane can do certain operations. I mean, in the control plane, we have a general purpose CPU, so we can do whatever we want there. So one example, this example will be developed in the lab, is implementing a MAC address table. So for those who are not that familiar with MAC address table, the MAC address table has some 2 or 3 columns. I like to say that it has 2 columns, but let's just, for the sake of this example, 3 columns to be even more precise. And at the beginning, when we power on the switch, think about a layer 2 switch, and we power on, this table is empty. So in one column, we will have destination MAC address, and we're calling this column key because we're using the terms that we use for programmable data planes. But you can think about destination MAC address. And the second column is the egress port. So whenever a frame is generated from H1 goes to the switch, and if the switch doesn't know about this device H1, once the switch receives the frame, it can populate this entry. Destination MAC address is MAC1. Port this frame is coming from is port 0. So this information is stored because later on there might be a packet that should go to H1, and therefore the switch will have the appropriate information to forward that frame to H1. Now we are using P4 tables, match action tables. So the action will be forwarding. And what we have here is the control plane. First, the data plane receive the frame and will only send the MAC address 1 and the port 0, port this frame was received from. And with that information, the control plane can add this entry in the forwarding table. Table add, action is forwarding or forward. The key is MAC1. The action data is port 0. Remember that the match action tables cannot be populated from the data plane. That's why it has to go to the control plane, and the control plane has to add this information. Similarly, when a frame is received from H2, the data plane will create a digest, MAC address, ingress port, and this information will be populated in the forwarding table. So that is a very simple application on how to use packet digest. Notice that we don't need to send the whole frame to the control plane, and therefore this is an appropriate way to implement or to use packet digest. So we will develop this example in lab number 11. This will be the last lab that we will be doing in this workshop. So we will have 2 hosts, programmable switch. This switch will be empty. We'll have a MAC address. We will implement a MAC address table. It's a match action table. It's has the role of MAC address table. We will create packet digest, extracting the source MAC address of packets and the ingress port, sending that information to the control plane, writing a small program that will be the controller, and then using runtime APIs to send information to populate the MAC address table. And then we will verify connectivity between the 2 hosts. So that's the plan for today. With that, I think that's pretty much all we need to know. And I don't see any questions. So what we will do next is we will start with lab number 9. This is the lab that we will be using registers. So Jose, are you ready to share your screen?
Sure. Thank you, Dr. Jorge. Hello, everyone. So let me share my screen. So we will start by, we will do lab 9 now. This is an interesting lab. It's simple, but we show all the features of what you can do with register. It's very basic. The only thing that we are gonna do, we are gonna store a value in that register, and we are gonna reach that value from the control plane. So I invite you to do this lab with me. So I will schedule a reservation. We'll go to the P4 application course, and I will select lab number 9. So let me go here. I will select a pod. Let me schedule the time, and I will enter the lab. Okay, I will divide the screen. I will undock this. And now we are ready to start. So as usual, we start with a brief overview of the labs. I will skip this part. We have an introduction in section 1. We explain basically what registers are. We present the basic operations that you can do with registers in the data plane. Then we explain the lab scenario. And after that, we are ready to jump into the activity from section 2. We can see here we have the topology. We have 4 hosts, and what we will be doing is we are going to use this P4 switch, switches 1, to store the last IP address, the last source IP address of the senders. So we are going to use register for that, and I will proceed with step number 1. We'll open mini edit. We are already familiar with these steps. In step 2, I will open the topology. Then I will run the emulation. After that, I will open a terminal just for the sake of completeness. I will run a ping test from host H1 to host H2. And we will verify that our before switch doesn't have any program running in there, so we shouldn't be able to forward any packet here. After that, we are ready to start defining registers. So to get started, I will minimize these screens and I will open the developing environment. We'll open the Linux terminal. Then I will open Visual Studio Code by running the following command. Once we are here in Visual Studio Code, we are gonna work in the ingress pipeline. So I will go here and I wanna explain what we have here. We are not gonna define the match action tables. That's already defined for us. I just wanna show you that we have, as usual, a table that will be forwarding the packets. We have two actions, forward and drop. And at the end, as you are already familiar, we have the apply control block. The ingress.before file basically is applying the forwarding logic. In step number 2, we are gonna define a register. This will be a single cell register, which means that we'll store just one value, in this case, the last IP address, the last source IP address to be precise. And we define a register by issuing the following statement. We call it register. We define how many bits will this register will contain. In this case, we will store an IPv4 address, so we need 32 bits. We know that this is a single cell register, so we just need we will use just one position in this register. It could be an array. You can add more elements. To know more about that, you might want to run lab 10 when we use a register array. And yeah, but in this lab, we are just going to use one cell. And after we define the register type, we give it a name. In this case, last source IP. And that's how we define a register. This is very simple, but it's very powerful, and we are going to see that in the next steps. After that, we know what we want to do. We want to store the last IP address, so we have to define an action to do that. So I will define that action. Action. I will call it update last source IP. We won't use any parameter from the control plane, so I will leave that empty. And what we are gonna do next, we are gonna write a value in the register that we define here, last source IP, and we do that by simply typing the name of the register, and we call the function associated to this register, which is write. And this function receives two parameters. The first parameter is the position or the slot or location of in the register. In this case, is 0, like the C language in P4. All indexes start at 0. And the other parameter is the value that we want to store. And we know that the source IP address, we can obtain that from the header.ipv4.source others. Okay. And as simple as that, we define an action that will store a value in a register. Okay. Then we have to execute this action. And what we are gonna do is we are gonna execute this action in the apply block. Let me go down. And you can see here that we are gonna call this action before applying the forwarding logic. And this is done by simply calling the action So, and that's it. That's how we execute an action, and this action will store the last IP address in the register last source IP in position 0. Okay, don't forget to save the changes, and after that, we are ready to test this program. So to do so, we are gonna compile the code by issuing the following command, before C, basic.before. We can see that the binary was generated, the basic JSON file. This is the file that we are gonna push to switch S1. In step 2, we're gonna do that. Push to switch. The first parameter is the file that we wanna send to the switch, and the other one is the target, which is S1. After that, we go back to mini edit. We wanna confirm that we have the binary in switch S1. We open a terminal. Let's verify. We list the files that we have here, and we can see we have the basic.json. And after that, we are ready to run the switch daemon. And we do that by issuing the following command that you can observe here. Is simple switch. We specify the interface 0 that is associated to the interface. Port 0 is associated to the interface S1 ETH0, and the other interface is associated to port 1. And similarly for port 2. And then we specify the name of the file, which is basic.json. And we state ampersand because we want the simple switch instance to run in the background. Let's see if I have any typo here. Okay. Press enter and we are already running the switch daemon. After that, we have to populate the match action tables. I will press enter to return the CLI. I will do that by using the simple switch CLI application. Simple switch CLI, and I will specify the directory where the rules are stored. So after populating the rules, we are ready to verify our before program. To do that, we are going to start by opening a window in host H2. I will open a terminal here. I will start listening on interface H2 ETH0. And then I will switch back to host H1. And I will run the following command to send a packet to host H2. Hello world is the payload. We have the command, the IP address of host H2, and the payload. So let's see if the program works. It works. We can verify in host H2 that the packet was received. So that means that our before program is working well, is forwarding packets, and there's no problem. So next, we are ready to read the values of that was stored in the register that we defined. We are gonna go back to the switch CLI, and I will run the simple switch CLI application. So I execute the simple switch CLI command, and then I will be able to issue runtime commands. To read the value, to read the value that is stored in the register, I will issue the following command, which is simple, which is register read. We specify the control block where this register was defined, which is my ingress dot the name of the register, which is last source IP, and we can also specify the position or the location of.
Yeah, just to clarify, Jose, it seems that you are getting all this information from your mind, but you have that in the lab manual. So could you show exactly where you are getting that? So somebody who wanna follow.
Yes, we specify, we provide a brief explanation of the commands in every step. And then we also provide a general background in the introduction. You can refer to the introduction to know more about these commands, which is simply, in this case, we want to read this value. So this is for the data plane. We know that we store these values in
And Jose, for example, the command that you were writing, could you go to the lab manual and pause for a second there? So what you were doing is you write on the left hand side, register read my ingress.last source IP 0. That's what it said, and that is highlighted in red on the left hand side. On the right hand side, that's exactly what you read, what you wrote. So that's what I wanted to highlight, because it seems that you're bringing this from somewhere. Just want to highlight that is over there, is on the lab manual.
Yes, I am referring to the lab manual here. So just to recap, we are going to read the value. We are going to issue this command register read. And we are going to read the value that we store in the register last source IP at position 0. So let's see. So we can see here that this command returned the following value. We got the register, we got the index, and we get this decimal value, which doesn't make it, maybe doesn't make too much sense, but this is the way that the V1 model stores the value. But let me go here. We are here, sorry. But this value that you are reading here corresponds to the IP address 10.0.0.1.
So there is a question from Italo. Jose, you specified the start position to read. So this is element 0. But how many bytes will be read?
Thank you. Thank you for the question, Italo. Yes, let me go back to the ingress pipeline. We define a register here. This is a register, and this register will store 32 bits value. So implicitly, we know that this is a 32 bits value. We don't need to specify the how many bits we want to read. That's already depends on how many bits we allocated in our P4 program for that register.
So it's going to be read 32 bits because that's the side of your register, correct, Jose?
That's correct. So let me go back to the step. Here we just read the value which corresponds to the IP address 10.0.0.1, and then we can verify by sending a packet from host H3. I'm gonna go and open terminal in host H3. I'm gonna use a send.py script. I will specify that I want to send a packet to, for example, host H4, as we have here, and the payload is hello world. we send a packet, and then we should be able to see the last source IP address by issuing the same command, the following command: register read my ingress last source IP and the index. So let me go back to switches 1. I will type that command: register read my ingress last source IP, and the index in this case is index 0. And we are seeing this, the output is the location, the control block where where the register last source IP is located. It comes with the index and the value that is stored inside that register, which is a decimal value. And that decimal value corresponds to the IP address 10.0.0.3. And that's how we can read values that comes from the control plane. Okay. In the next section, we are going to show that we can also write values from the control plane to registers. So what I will do is I'm gonna write a value in the register that we defined, last source IP, by issuing the command that you can see here on the left-hand side: register write my ingress last source IP. We specify the index and we specify the value that we want to store at that specific index. So let me write that value: register write my ingress, which is the control block, the register last source IP. I want to store the value 321 in index 0. So that's what I am specifying here. And press enter. We will verify in step number 2 that we store that value correctly by issuing the following command: register read my ingress last source IP. And we specify the index. So let's verify. We can observe that we successfully stored the value 321 into the register last source IP at index 0. Then in step number 3, we have also another command, which is resetting the value. We can clear the value that is stored in a register from the control plane by issuing the following command: register, the command is here, register reset. So with that command, we should be able to reset the value. This will set the value in the register last source IP to 0. So let's verify that. In step number 4, what I will do is I will read again the value, but in this case, the command changed a little bit. Notice that in this register read my ingress last source IP, we are not specifying the index. So let's see what's the output there. Register read my ingress last source IP, and you can observe that the output says that the register index is omitted and we are reading the entire array. In this case, we can observe that my ingress last source IP is clear, is set to 0, but this is something very interesting and will be further explained in lab number 10, which is where we use a register array, but this is the command that you will need to read all the values stored in a register in case this is a register array. And with that, we are done with this lab, and I hope it was interesting, and I will be happy to answer any questions. Yes, Italo. Please go ahead. You can unmute yourself also if you feel more comfortable.
Yes, Jose, can you hear me?
Yes, I can hear you well.
Just one question, please. So when you have a 32 bits register, and let's suppose that you do like an increment on the register. So what happens if you have like an overflow of the register? It's going to be resetted. It's going to be an error, an exception. Do you understand what I mean?
I understand. Truly, I don't have experience with. I didn't have that issue, but these are registers that are implemented usually in an ASIC. So what will naturally happen, I think, is you will restart the count if you are using the register as a counter. If you reach the highest value in what you can represent with 32 bits, it will restart again from 0. That's what I anticipate.
Thank you.
All right. Is there any other questions?
Hey, hi, Jose.
Hello,
Can you hear
Vinicius.
me?
Yes, I can hear you well.
Okay, yeah, so I have one question here regarding registers. I'm wondering if they are atomic. Are those writes and reads atomic, or are they vulnerable to race conditions or any sort of concurrency issues that can happen?
Yeah, go ahead, Lee.
Yeah, so this is a very good question, actually. It depends on the target. For example, if you deal with the hardware, whenever you perform a register read, there's a flag there that is called from hardware. You set it equals to true or to false. And you have the option to basically make sure that you are reading directly the last value of it, or have like a batch reading where you can get kind of like a shadow version or a copy of the previous values there. So you have the flexibility to control that in the hardware. And by hardware, I'm talking about Tofino here in this case. Now in the software switch, basically because it's software, I think you might have some race conditions here. So you might be reading a value that is not updated.
Got it. Thanks for the information.
No problem.
Well, thank you for. Go ahead. Sorry.
Yeah, follow up on that question, please.
Mm-hmm.
So, for instance, on Tofino native architecture, since we have multiple pipes running at the same time, when we define a register on our P4 program, is that register tied to a one specific pipe? Is that shared among any specific pipes? Because following up on the Vinicius questions, for instance, so suppose that you receive two packets pretty much at the same time and two pipes are working on the same register. I'm wondering if that is also like a vulnerable for race conditions or not, if we are supposed to have different values on which one of the pipes. I don't know if you understood the point.
Yeah. So I think like this question is like more Tofino or TNA specific. I can't give you like a very accurate answer. I'm sorry about that. But I think that because you have these different types you were mentioning, they will have their own resources, so you won't be able to share them. But again, I'm not 100% sure about this. This is more like a architecture specific question.
Yeah. On behavioral model, I think we don't have like this concept of different pipes, right?
Yeah, no, there's no such thing here.
Yeah, thank you.
No problem.
Well, thank you for those questions. I don't see any other questions. Well, thank you, Jose, for this lab. Yes, Ali?
Yeah, I just want to add like an additional observation. The command that Jose wrote, the clear for the register, that will be clearing all the entries in the array. And if you are interested in clearing a single one, you can also do that. And the other observation, which might be also useful for that indeed, so you are using here the index 0 because Jose did this register array with only a single element. Typically, and this is something that Dr. Jorge mentioned at the beginning of the slides, typically you want to have an identifier. For example, a good way to do that, if you have a tuple of fields that will represent some unique identification, for example, for a flow, we know that the flow has the source IP, destination IP, source port, destination port, and protocol. This is what they call the 5-tuple. But because you have multiple fields, you can't use them as a directly as a one index, because if you remember in the code, you have this 0 or 1 or 2 all the way up to how many elements you have in the array. And so way around that is to use a hash function. And if you use a hash function, you can basically, and when I'm saying hash here is not the cryptographic hash, it's the regular hash, which is basically you apply a mod or modulo operation on the length of your array. So you're going to end up with a value that is between 0 and the last element in your array. And therefore you can use that as an index. And of course, because you are using hash, you might be subject to collisions. And there are ways around that. So it's either by enlarging your array size or maybe creating multiple arrays. But definitely, it's useful to have multiple fields when combined to represent a single index. And hashing is like kind of the usual way that people use to basically achieve that.
Thank you, Lee. And where is there any lab where if somebody wanna explore more that?
Yes, actually, we explained that in lab number 10. We implement a hash table to calculate the inter-arrival time
Jose,
of a flow.
I think since we have some time, maybe just share the content and they can see it there.
Sure, I am having it right here. So, okay, let me go here. Let me show you. I will just go to the cyber training website. I will open the lab manual here on the virtual labs on before data plane applications, the library that contains that lab. I will jump to lab number 10, which is calculating inter-arrival times, the inter-arrival times using hashes and registers. And here we actually implement a register array. And we explain here in section 1, as usually, the background for this lab. We explain how to declare and use register arrays, and we will also show how to calculate hashes, because this hash function is the one that we are going to use to identify as a unique identifier for a specific flow, and we are going to use the output of that function as an index and that's a way that we can implement a hash table using a register array. And actually, that's exactly the scenario in lab number 10, where we hash the source and destination IP. We extract the previous inter-arrival time, as Dr. Jorge was showing in the slides. We compute the time difference, we update the time value, and then we insert that value into the packet so we can read that on the destination. So yeah, I invite you to take a look on lab number 10, where we covered that topic. I don't know if there anything else, Ali, that you want to add.
Right. Thank you, Jose. Thank you, Eli, and thank you for those very interesting questions. I didn't see any more questions, so it's Ali has a comment. I just found a GitHub issue on P4 concurrency. This might be useful. Ali, you are sharing this in the chat window. Thank you. So let's have a break. And before we go to the break, what we will be doing next is we will have the next lab hands-on session. Lab 11 is how to communicate from the data plane to the control plane. So that's what we're going to be having after the break. So right now is 9:55 Pacific time. We will be back at 10:05 Pacific time. So we will be coming shortly. All right, we're back to our second session, and Ito and Vinicius, you were having some very good question. I was looking online about that information. There is a course. We at USC attended this course. 1141, if you are associated with Intel Connectivity Academy, probably this is the best place for those type of questions related to race condition in Tofino native architecture. I was looking our notes. It seems to me that the 2 or 4 pipe, depending on which model, they work independently and they cannot communicate. They can only have some communication through the traffic manager, but I'm not sure either as Eli. Eli, I don't know if you have anything else to add. I think this is the best course for very specifics of Tofino ASIC.
Yeah, indeed.
Yeah, that would be my suggestion. And Vladimir is offering this from time to time. I think at least twice per year. All right. I will put this in the chat window, by the way. Okay. So we have our second lab of the day. Eli, are you ready to share your screen?
Yeah, absolutely.
Okay, let me pause.
All right. Thank you, Dr. Jorge. Hello, everyone, again. So in this session, we're going to be doing a new lab related to packet digests. And this is going to be lab number 11 in the lab series. So I will schedule a lab for myself. And then make sure to select the Before Applications library. And there we have lab number 11. Then I will make a reservation. And then enter to our lab. All right, now the pod is ready. So as usual, we will undock the lab manual, put it on the left-hand side and the platform on the right-hand side. And let's get started. So the idea of this lab is to see how we can generate notification messages from the data plane. And as Dr. Jorge was saying, there are different ways to do it. We're going to be using packet digests because they are a very efficient mechanism to push only the needed information to the control plane. Like any other lab, we have a table of content, overview, objectives, credentials. And then we have the intro, which describes the idea of communicating with the control plane and specifically what are digests. And so as a quick review, what we're going to implement is a scenario where we have a single P4 switch and 2 devices, H1 and H2, 2 end hosts. And we're going to assume that the table is not populated. The match action table for forwarding is empty by default. And as soon as we receive a packet or a frame, if we are assuming this is a layer 2 device, from any of the hosts, we will record their MAC addresses and then send them as a notification to the control plane using digest. So you can see here we are sending the MAC addresses and the port from which this frame comes. So for example, here port 0. And then our control plane will be basically adding a new entry to the forwarding table by using the information that we sent here. So by the end of the lab, we should be able to have full connectivity between the end hosts without having to go manually to the control plane interface and populate the tables there. Okay, and this concept is known as Mac learning. You probably have seen it in all the networking courses. So we are learning the Mac automatically by listening for these packets at the switch or these frames. All right. So the topology has one switch, two end hosts. So let's get started. I will launch mini edit by double clicking on the icon on the desktop. The password here is password or small caps. And there we're going to open the topology of lab number 11. So file, open, lab 11. And we're going to select the topology here. And we can see it now as one switch to end hosts. So everything is ready. Next thing we have to do is start the emulation by clicking on the run button. All right, now the topology has started, the emulation has started, so we can proceed by implementing digest and writing the P4 program. The first step here is, as we were doing in the previous labs, just to make sure that we don't have connectivity by default. And the way to do it is we're going to go to host H1's terminal, hold the right click on H1 and terminal, and there we're going to issue the command ping 10.00.2, which is the IP address of host H2, and I will send 4. And we can see that there's no connectivity, and this means that the switch has no data plane specification, no daemon is running, and this is what we're going to be doing later on in the lab. Okay, so section number 3 is about creating these packet digests in P4. Before doing that, as usual, we're going to start by loading the programming environment. So first we have to start a new terminal, and to do that I will minimize all the windows, and then I will click on terminal icon on the desktop, and from there we're gonna start the Visual Studio Code and specify the working directory, which is P4 labs and lab 11. All right, so what we can see here is we have the files as usual there, but we have an additional file, which is the controller.py. And remember that the goal here is to write digests, right? To implement digests. And to do that, you have to implement it in 2 different places. The first one is in the data plane, and the second one is in the control plane. And this is going to be the only lab in the series that is different in the sense that we are also writing a Python program so that we implement the controller or the control plane. All right. So to be able to use packet digests in P4, the first step we have to do is to define what are we gonna push to the control plane. So this digest, what kind of information this digest will contain. Now, if you remember in our code, we are doing MAC learning. So we want to learn the MAC address of a certain device. And therefore, the digest should contain the source MAC, right? You can see it here. We have source address 48 bits. That's the size of a MAC address. And the other information that we want to know is from which port this frame came, right? In this case, this is the input port. And the input port by default, the V1 model has a size of 9 bits. So that's why we are creating here bit 9. All right. And because we want to push both of them, the way digest work is that you have to enclose them into a struct, similar to a C struct, right? So we write struct, we give it a type. So this is digest_t, and the information that is going to be pushed with that digest. Okay, in this case, the source MAC and the input port. So let's start by typing in this piece of code here. Struct digest_t. And then inside that, we want to add 48-bit field which corresponds to the source MAC, we call it here source address, and another 9-bit field, which corresponds to the input port. We're calling it here in_port. Okay. So now we defined how our digest will look like, what kind of information this packet digest will transfer or will contain. The next thing we have to do is we need to initiate an instance of this digest type. So we created the type now. The next thing we have to do is we have to initiate that. And whenever we initiate this digest type, it should be declared within the metadata. Now, we didn't talk much about metadata. We only talked about the standard metadata. And the standard metadata, as we were talking about yesterday, these contain some information related to, for example, the traffic manager, the port from which a certain packet came, or how to specify an output port, and so on and so forth. These are the standard metadata, also known as intrinsic metadata. Now, in this example, we are using what we call user-defined metadata. So there is a way in P4 to have your own metadata that will contain some arbitrary fields. You can create whatever you want to have in this metadata. And the goal of this metadata is to have access to the data that you enclose in it throughout the pipeline. Let's say you have something you want to transfer between two different blocks. You can put it in your own user-defined metadata, and this is going to be available for you in different blocks in the architecture. Okay, and we are creating another struct here called metadata. It's already created for us. In the previous labs, we were keeping it empty, but now we're gonna add to it an instance of our digest. So digest_t mac _learn digest. So this is the name that we're giving it, right? Mac learn digest is an instance of the digest type, which contains the source Mac and the input port. All right. So this is what we need to define in terms of the headers or the fields or the metadata. This is all that we need to have in terms of declaration of or implementation of a digest. So I will go ahead and save the file by pressing on Control-S. The next step is to work in the ingress pipeline. So we need to modify the ingress.p4. And this is where we have to really think about what is the right way to do things. So how are we gonna instruct the control plane, right, to basically add this entry into the forwarding table? So before we do that, let's look at how the ingress looks like before we do any changes. So we have a table called forwarding. The table matches on the destination MAC address. So you can see here destination address inside the Ethernet header. We have an exact match, and we have 3 associated actions: forward, drop, and no action. And the idea is whenever we receive a frame, we're going to look at the destination MAC. If it's in the table, we're going to apply the forward, and the forward will set the egress spec of the standard metadata or the output port to be equal to whatever value we pass from the control plane, right? And otherwise, we can invoke the default action. Here the default action is drop. So we're going to be dropping the packet. So we are just implementing the basic forwarding, or actually it's already implemented. But what we're going to do is we're going to create an action so that we can define how we are transferring the digest to the control plane. And this action, we're going to call it learn_mac. So we can add that in our my ingress block. So let's add it here below the forward. And now I'm typing this block of code here. So action, we give it a name. We are calling it here learn_mac. We have no parameters from the control plane, right? And why we are passing nothing from the control plane? Because the destination MAC is already in our headers, right? And the input port is part of the center metadata. So I need nothing from the control plane to be passed to this action. Okay. So how are we gonna push this digest to the control plane. There is a function called digest, which is provided by the architecture. All you have to do is just pass to it an instance of the digest type that we created before, right? But before we do that, we have to make sure that we actually fill these fields inside our digest. Okay. Now, how can we access these two fields, the source address and the input port? So remember that these are part of the digest, and the digest is part of the metadata, the user-defined metadata. So if we go to the ingress block, we can see in the definition of this control, which is the my ingress, that we have a metadata here called meta. So this meta here is an instance of the user-defined metadata. This is different from the standard metadata, which we've been using in the previous labs, which are an instance of the standard metadata type. Okay, so to actually access those fields, first we have to start from top to bottom or from high level to specifics. So we start first with the meta. Inside that, we have the Mac learn digest. So meta.mac underscore learn underscore digest. And inside it, we have the source MAC address or source address. So we need to assign to this field the value that is present in the Ethernet header, specifically the one that is in the field source address. Okay. The next step is to assign the other field, which is also part of the metadata Mac learn digest, but this one is called now the input port or in port. And the value we're going to assign to this one is the ingress port that came from our standard metadata. So standard metadata dot ingress underscore port. Okay, so at this point, we specified the values of these fields in our digest, right? And we got this information from the header and the standard metadata. The next step that we have to do is we need to push this information to the control plane. And the way to do that is simply by typing digest. So this is a predefined function available in the architecture. It receives two parameters. So the first one is the receiver, but in the V1 model, this is not implemented. So it doesn't matter what value you put here. Okay, we're assuming one receiver here. It's not implemented to have multiple ones. But what is important is the second parameter. So the second parameter is of type struct, right? Struct and digest type specifically, right? So this is gonna be meta.mac learn digest. So note that we are pushing now the whole Mac learn digest, right? Which contains both the source Mac and the input port. So in summary, this one here, the digest, this function is the one that's gonna be issuing the push to the control plane. Okay. All right, so now we have the action. The next step is to create a table. And this table will be using the learn Mac action. So now let's define this table and I will describe what we are doing here. So table Mac learn, that's the name of the table that we specified. The match field will be our the key, which is basically the source address. So header dot ethernet dot source address exact. So why are we matching here on the source address? The idea of this table is to basically every time we receive a packet from or a frame from any of the hosts, we look at the source MAC. We see, is it already in that table? If yes, it means that we already learned this MAC address, so we don't do anything. Now, if it's not in our MAC learn table, it means that this is a new host sending, and therefore we have to basically push the digest so that the control plane will add it later on. Okay, and we can see here that we have two actions associated, learn Mac, which is the one that we just created, and the second is no action. And by the way, we've seen a little bit no action in the previous labs, but this is an implicit action that is created for you. So you don't have to implement anything called action, no action. This is already there. And the idea is you do nothing in that. This is like you created an empty action, has no instructions in it. All right, so the actions here are learn Mac. So that's the first one. And the second is no action. Now, we can specify a size. Let's put here 32. And finally, and this is very important here, what is the default action? So if we remember from when we talked about match action tables, the default action will be invoked whenever we have a miss. So this means if we want to read this table, let us match on the source address and the Ethernet header of a certain frame coming to the switch. If we already have that in the table, we're gonna later on be saying that we need nothing from it, right? So we add an entry to no action. Otherwise, if it's not there, so we don't have a hit, we have a miss, execute the default action, which is gonna invoke the learn Mac action that we created here. And there, this is where we're gonna extract the fields and we're gonna push them as a digest to the control plane. Okay. If there's any question, just feel free to interrupt me, please.
Yeah, there is one question, Eli. Vinicius, does the digest native function provide any retry capabilities? I'm wondering what would happen in a case of a remote controller is being used and the connectivity isn't reachable temporarily when it's trying to push.
That's a very good question, actually. I'm not 100% sure, but I think that if it misses this specific function or this specific digest, you have to manually redo it. But I can look that up as after I finish this lab, and I can see if there's another way that is implemented. And that's a very good and I think useful feature to have.
Yeah, thank you, Lee.
All right. So now we have the table ready. The next step that we have to do is we have to actually invoke that table or apply that table, right? And this is typically done in the apply block. So all we have to do is before we do the forwarding, just add the Mac learn table.apply. So we are adding it here before forwarding. Obviously, this is not the only way to do it. You can make it a little bit more optimized. So maybe you want to forward only if there's a miss there. So we know how to do that. Just write an if statement, and then we only forward if it's not if there's a miss in the Mac learn. Right. All right. So basically that's it. This is all we have to do in the P4 side. So in summary, we create first the type of this digest, which is a struct. We specify what are the fields that we want to push. Then we add an instance of that digest to the metadata. We fill the information in some action that we create, and then we invoke the digest function that will push this digest to the control plane. Okay, now the way you want to invoke this digest is completely up to you. Maybe you want to, for example, in one of the research that we've done, we were pushing some statistics about the links and the traffic conditions. And you can have maybe a timer that you implement in P4 that says maybe every second send a digest to the control plane, or that's completely customizable up to you. Okay. All right. So this is the data plane side. We're done here. The next step is to program the control plane or the controller application. So as I mentioned at the beginning, there's a program called controller.py. And this looks a little bit scary as the first time you look at it. But basically what happens here is that you have a skeleton Python program that will connect to the thrift, or using thrift will connect to the switch. So in the previous lab, Jose was showing simple switch CLI. Simple switch CLI is a similar program to this controller.py that is connecting to the software switch, the the daemon using thrift. You can see here there's all the connection information, right? And then after that, you'll be able to issue any command that you have in the simple switch CLI. You can issue it here in Python. So we already wrote or provided this code for you because this is kind of general, and I was saying it's like a skeleton code because you don't need to change anything here, even if you are writing a program for a completely different purpose. All you have to do is know how to receive this digest, and once you receive this digest, how you can perform some table add function so that your table is populated, right? But same thing that, you know, you have access to table add, you have access to read, you have access to register operations, counters, and so on and so forth. So everything that you see in the simple switch CLI, you can execute it from this Python program. Okay, and so what we're gonna be doing here, if we just look at the structure, we have a main function, right? This main function is making sure to connect to the switch, right, to the daemon. And then we have another function called listen for digest, which we also created. And we have another third function called on message receive. So whenever we receive a message, what do you want to do? And we're gonna be filling all the code related to these functions, right? And at the end of the Python program, you have an invocation of the main function. So we're invoking main, and all the other functions will be invoked correspondingly, right? All right, so let's start first with the listen for digest. So here, and before I start with the coding, I just have to mention that the digest is implemented very different in different architectures, right? So here we are using socket communication to pass the information of the digest. Other architectures might be using a different ways to do that, maybe through a direct memory access or DMA. But let's just now focus on BMV2. And you know, if the same code with slight modifications in the P4 side will be applied to other architectures as well. Okay. All right. So in the listen for digest, what are we gonna do here? So we're gonna insert this block of code, which basically says that I want to create an infinite loop and then listen for messages, right? So I have this sub here, which basically connects to the socket and subscribe to a certain to the messages that are going to be received through the socket. And once we receive this message, we're going to be parsing it and do further things and next steps, right? And if you are familiar with socket programming, this is very common to when you create a TCP or UDP socket in Python or in C, and you have this hanging instruction here that waits for a message to be received, right? So we have message equals to sub.receive, and you know, this is Python, so we don't have to define, we can immediately assign to a certain variable. So I'm assigning to message here whatever is received through the socket, and this is where the program will be hanging and waiting for new messages. So if no messages is received, the program will be always hanging here. Once we receive a message, then the next instruction will be executed. And in our case here, we're going to invoke this function, which is called on message receive, right? We're going to invoke this function, and we're going to pass to it two parameters: the message that we received, and the second one is an instance of the controller, right? Because later on, we're going to be adding table entries, so we need to have an instance of the controller. All right, so that's all what we have to do here. We wait for the message to be received, and then we invoke the on message receive function. Next, we have the on message receive, and we can see here, these are the two parameters that we sent. Here it's called MSG instead of message and the controller. And at the beginning of this function, you have a line here that we already wrote it because this is also common to all digests. So no matter what kind of values you pass in your digest, you have to issue this first line. And what are we doing here? Basically, this is there are some metadata that are associated with the digest. This includes information related to the buffer, and I'll explain what a buffer is next. But what we really need from these set of variables is the num. What is num? So imagine a case where you have this topology, right? You have one switch, one P4 switch, and the end hosts. So what if there is a plenty of and a lot of hosts that are sending at the same time, right? So what happens is, if really at the same time or very close in time, we receive two frames. So what's going to happen is, instead of sending two different digests, the P4 program or the data plane will basically have a buffer that will contain, it's like an array that will contain multiple digests that are pushed at the same time, right? So if I receive a frame from two end hosts at the same time, I might have the content of the digest that I receive here contains two entries, not only a single entry. And this is a very good way to deal with having digest being missed by other by the data plane because it was busy sending the previous digest to the control plane. So it's a way that you can combine multiple digest in a single packet digest message and send it to the control plane. It makes it more efficient, it makes it faster. And on the control plane, it's Python, you can do basically whatever you want there, right? So you can parse them manually, loop over the entries, and perform the action that you need, right? And so num here, this specific variable will tell us how many of these digest messages were received. Okay? So, all right, so the next thing we're gonna do is we need to basically remove the first 32 bytes from the message, because the first 32 bytes are already here and are already parsed. So I want to make sure to get rid of the first 32 bytes. And the way to do that in Python is just by, this message is kind of like a, it's an array of bytes, right? So I'm saying take from the 32nd byte onwards. So remove the first 32 bytes because they were already taken for these specific fields that we have here. Okay. All right. The next step that we're going to do is we want to define how many bytes we are taking from this digest. So let's go back to our P4 program, to the headers. And what we can see here is we have the source address. This is 48 bits. 48 bits is, this is 6 bytes, right? And then we have the input port, which is 9 bits. So this is 1 byte and an additional bit. So if we add 6 plus 1 byte plus additional bit, this is going to be 7 bytes and an additional bit. But because we have this additional bit, we have to make sure that we take an additional byte so that it will contain that additional bit. And therefore, we are now declaring a new variable here called offset that will have the value 8, which means that we will be receiving 8 bytes. Now, if you are creating a digest that will contain different information, make sure to count how many bytes that are there and write it here in offset. And why do we need that? I will explain next. All right, going back to the controller. So let's type in offset is equal to 8. All right, next we're gonna type in this code here, which, it's a little bit too much of code, but unfortunately, that's the only way to do it. You have to, if you want to write a fully, fledged application, you want to learn at least a programming language like Python or C, and you should be able to express whatever you need to do there. And in this case, you want to receive the digest, and we're going to be invoking functions to add entries in the match action table. Now, so what are we doing here? So I will explain as I type in the code. First, we will be creating a loop that will, so for m in range num. So we are assuming that we might receive multiple digests at the same time, right? And this is why I'm creating a loop that will iterate on the number of digests that we receive. And again, this will only be executed if 2 of them will be received at the same time, and then you are combining them into a single digest message. All right. And now there, what we're going to do is we need to unpack this message, right, and store the results in the variables that are the MAC address and the port. However, we need to unpack this information from the message, but we have one field which is 48 bits or 6 bytes. And we're using this Python library here, struct, and I have it already open. And if you look at it, what you can see is the information that you want to parse here will contain, will have different sizes, right? So for example, short or unsigned short, these are 2 bytes, int 4 bytes, unsigned long 4, long 8. But as we can see, there's nothing here that is 6, right? So we don't have a 6 byte type here. And so instead, what we're going to be doing is we're going to use 4. So L here, if I go back to the table, L here is 4, right? So these are 4 bytes, right? And then I'm going to use H for 2 bytes. So these are 6 now, right? 4 plus 2. And then the first 4 bytes will be stored in a variable called MAC1. The second here, H for the 2 bytes, is going to be stored in MAC2. And then we have 2 bytes, which are going to be stored in the variable port. Okay. And you can see here you have this exclamation mark at the beginning. This is just to define like the encoding. So here in this case, this is big Indian. But this is always going to be the case here with digest. Right. So in summary, we specify the bytes, right, using these codes here so that we can unpack the struct that we receive from the data plane. Next, we're going to specify for the unpack function the message object, right? So we have this message. We're starting from byte number 0 all the way to offset. So this is where we're using the offset, right? We're starting from byte number 0 to byte number 7, right? Because this is Python, so we exclude the last field. So it's as if you are having from 0 to 7, which are 8, right? And then we unpack them and we store them into MAC1, MAC2, and port. Okay, this seems a little bit complicated, but it gets easier with practice, right? All you have to do is make sure to specify the fields here in this string to correspond to the sizes that you have in the data plane. And I have to mention with other architectures, for example, Tofino, and I have to admit that working with digest on the control plane is easier than this one, right? So you don't have to care much about these sizes. It's going to be provided for you. All right. Okay, so let's type in this sentence. And remember that we are now dividing it into the MAC address, we're dividing it into 2 fields. So MAC1, comma, MAC2, and then port. All of those are equal to struct dot unpack long, and then we have HH for 2 bytes, comma, message from 0 to offset. Okay. So now that we have these we have here 4 bytes, 2 bytes, and 2 bytes, but we care about the MAC address as a single variable, as one variable. So how are we going to do this? So we need to convert these into a single 6 bytes variable. So I'm going to create a new variable here called MAC address. And what we're going to do here is we will take the first 4 bytes, right, which is MAC1, and shift it to the left 16 bits. So I'm shifting this variable 2 bytes to the left. And then after the shift, what I'm going to do is I will add to it MAC2, the remaining 2 bytes. So in other words, what we are doing here is we are combining the portion of the MAC1 and MAC2 extracted from the struct so that we can represent one MAC address, which is 6 bytes or 48 bits. Okay, and it's a nice example because it shows you some, fields that are not, conforming to the ones available in the struct struct library. So it makes you understand what you are doing here. Okay, so after we extracted this MAC, or we calculated this MAC, we can use print function in Python to just display it. So for example, MAC address, this is equals to, we know that we use comma here in print so that we can concatenate, right? So string MAC address, and then we have port. Let's add here colon, and then string port. So this is just for debugging purposes so that we see the values that we receive in the control plane. All right, so now that we parsed this information, what we need to make sure to do is we need to now remove or get rid of these bytes that we parsed, as we did in the in line number 47 here. And how many should we get rid of? We need to get rid of 8 bytes because that's what we parsed. So message is equal to message offset and then colon. It means start from the next 8 bytes, right? And so when you do that and the loop continues here, you're going to be parsing the next fields here so that you can obtain the MAC address and the ports. All right. Okay, so at this point, now we receive this information. We have them in Python. The next step would be to basically add these entries to the match action table so that they are populated with the forwarding entries. And remember that we passed an instance of the controller here to this message receive. And we passed that for this specific reason here. So we have controller, and we can invoke these functions that are available to us through the API, right? So one of them is do table add, do_table add. This is similar to the table add function that you were using in the simple switch CLI. What you specify here is you need to specify, of course, the table name, so which table we are talking about. So MAC learn, and then the action. And what we are doing here, we are adding an entry for a certain MAC address, and we are just using the no action for that specific action, right? And I will go back later on to the P4 program to re-explain what's happening as a whole, because there's a lot of small pieces that should be glued together at the end. So we are now adding to MAC learn using the action no action, and then we're going to concatenate here using the plus sign. We're going to specify here the key, which is the MAC address that we just computed here, or the one that we received from the digest. Okay. And because we don't have any action data, we still have to type in this arrow that we've seen in the simple switch CLI, but we don't have to add anything after it. Okay. So let me repeat what we have here. Do table add. We specify the table name, the action, the match key, which is the source MAC. And then finally, we have to specify that, this arrow, because usually if you have action data, you would specify the arrow and write the action data next to them. In this case, we don't have this kind of information. So we just write arrow and we keep it empty. Okay. Next, so we added this for the MAC learn so that we don't keep pushing all the time to the digest to the control plane using digest once we learn about that MAC address. But also we have to push to the forwarding table so that we can do the actual forwarding. And so let's first start by typing this print statement just for debugging purposes to see the information on the terminal when we launch the controller. So print forwarding, this is the table name, and the action is forward. Then we concatenate to it the MAC address, and we have the arrow here because we are specifying some action data, and then we have the port. So again, I will go over, once I finish this block of code, I will also show the P4 program next to it and explain what is going to happen. Okay, so this is just for printing. The next step is to actually do the pushing to the table, which is the controller.do underscore table underscore add. So here we have forwarding. That's the table name. The action is forward. And just like make sure when you type this kind of statements here, for example, you have to have a space because in Python, if you concatenate using the plus, it will just add the string directly next to the previous one, right? So, and if you write forwarding forward and you don't have a space, you're going to end up appending the key to forward, and this is going to give you an error. Okay, so forwarding forward, then string MAC address, and then we have an arrow, right? And then we have the port and an empty space at the end. Okay, so this is what we have to add every time a message or every time a digest is received. So let's see how the flow of information is here. So if we go to the ingress, let's say we receive, let's assume that the tables are empty at this point. Okay, and so we assume that host H1 sent a packet to H2. So now this is received at S1. So what happened is maclearn will be applied. If we go to maclearn will try to match on the source address, source MAC address. But because it's empty at this point, there's nothing there. So what's going to happen is we're going to invoke the default action, and this is going to call learn MAC. So we go to learn MAC. We are assigning the fields to the digest, so the source MAC and the input port. So we are specifying from where the frame entered and the MAC address. And we are invoking the digest, which will basically send this notification to the control plane. At this point, if we go to the controller was previously hanging here. Once it received the message, so now we skip this and we go to the next statement, which is on message receive. We go to on message receive. We first parse the first 32 bytes, right? We get rid of them, and then we iterate over the entries. In this case, we have only one digest. So num here would be equals to 1, and this loop will be executed only once. We unpack this information. We have them in Mac1, Mac2. We perform some arithmetic here just to have a final version of this MAC address. We modify the offset so that we take the second one in case there's another entry. And now, most importantly here is we add to the table maclearn using the action no action a value or an entry for this specific MAC address. And so why we're doing this, because later on, if we assume that the same host sent again to the switch, right? So this is going to go to maclearn. Maclearn will match on the MAC address, but at this time, the default action will not be executed because we associated an entry with the no action. So this one will hit, right? And therefore, we are not resending all the time this information to the controller. Okay? And this is a no action because really we don't need to do anything there. All right? And so after we did that, we also added to the table forwarding, because remember, we have two tables. So forwarding will be invoked. And we added here the MAC that we received previously, which was the source MAC of that frame. We added here as a match key as the destination address. So it means that later on in the program, if a frame entered to the switch that has the destination MAC address equal to the source of H1, let's forward it out of this port so that it reaches H1. Okay? And we're going to do the same thing for H2, right? So you receive from H2 and you do the exact same procedure so that you populate the tables. All right. Is there any question so far? I know it was a little bit too much to process.
Hey, Lee, as a matter of fact, I do have one question here. I do realize that this example is just for a learning switch here, but hypothetically, if that's struct digest, what if in this case the user wanted to also include like the switch identifier? Is there any native function that you could use to uniquely identify the switch and also send the switch identifier in that same digest?
So yeah, that's a good question. I mean, you have some information here. You can see the first two, we don't even have them here. So I don't know exactly what are these first two. You can look at the way this message was structured. It might have something related to the switch, and I think it does. But let's say worst case scenario, it's not there. What you can do is basically add to your struct here a switch ID, right? So you can kind of define it on your own, make it, let's say 8 bits. If you are assuming you have a total of, this is like a little bit too generous of 8 bits, right? Because you can represent 256 switches, but whatever field you have, you add it here and then you push it along with the digest, and there you parse it and you know which switch you are talking about. But again, I think that, and I can also verify it, these first two fields might be related to the switch ID. I will verify that and will let you know. Worst case scenario, you can implement it from scratch.
Got it. Thanks.
And I think we have an observation from Italo. You can pass the connection information to on message receive. Yeah, absolutely. Yeah, it's a good point as well, because we are connecting here through a certain socket to a specific daemon, so a specific switch, and maybe we have that information here somewhere, the ID of that switch. We can pass it to the on message receive as a third parameter and parse it and use it. That's a good observation.
Yeah, Eli, just another comment. So I didn't know about the digest message, and I was looking at the P4 specification. It looks like it's something more generic. So even Tofino native architecture, it might support the digest information. I think you mentioned that as well. So the comment that I was going to make is trying to correlate digest with the packaging message. Both of them are like the stream message, right? So, but the difference between the digest and the packaging is because on the digest message, you can group multiple messages into the same structure. And also you don't have to include the whole package.
Exactly. Yeah, that will save some overhead of always sending the headers if you want to forward it like a regular packet. And I think Dr. Jorge was talking about that in the slides. Here we are just pushing the relevant information. And yeah, the other big advantage here is the capability of the data plane to have this buffer and include multiple digests in case they needed to be pushed at the same time. That really makes it more compact and will minimize the overhead of basically keep resending and having this. Remember, this is an asynchronous kind of thing, right? So you always have to wait, receive, and then wait, receive. So it makes it a little bit easier to send a bunch of information in one digest, for sure.
Thank you.
Yeah, thanks. And yeah, you were talking about the Tofino. Even though it's in the specification, you were saying that it's more like a language thing. My experience is when I use digest on Tofino, it's a little bit different in the sense that you have to put it somewhere in the blocks in your pipeline, and specifically there's something called the ingress deparser. So you have to instantiate it there, and you don't have this function similar to this one here, which is called digest. You have basically, let's say you have maclearn digest. This is an instance. You write it, and then you write dot, and then there's something called pack, and you have to use that information to pack the fields that you want to transfer. So that's a good point that you mentioned, that it's written in the specifications, but in reality, when we talk about different targets and architectures and hardware, most of the time there are things that are specific to the vendor that they don't exactly follow the specification. They might implement things on their own way. And on the control plane side, so when you receive the message, there is something called a callback function. So you'd implement it. I'm talking about Tofino now. You implement it there, and then you parse, right? And so basically, you don't have something similar to what we did here with the socket, because I believe it doesn't use socket in Tofino, right? And what you have to do is you have to have a statement that will register a callback function. And this callback function will be executed every time you receive a digest from the data plane. I hope that answers the questions. I think we have another observation from Vinicius. So Italo, if it reconnects, the connection tuple would change, right? I was thinking in a case where it would always give to us a deterministic ID like the data path ID from OpenFlow. Italo, you're free to answer him. But if my take on this is, I think what Italo is mentioning, what we are doing first in the main, which we didn't go over like every statement, but we are connecting to the daemon of a switch. And so basically, if you have two switches, you need to do two connections. One connection for switch 1, one connection for switch 2. And that's how you can have like an ID that will uniquely identify a certain switch. But Italo, feel free to correct me if that's not what you were saying.
Yeah, no, it's basically like this, but trying to explore a little bit of the Vinicius comment. I believe one use case of what Vinicius is talking about is if we think about the management plane with multi-homed connection. So for instance, you have two connections to reach the controller, and suddenly one of the management connections goes down, and then you have a reconnect from another IP address, another provider. Maybe it's interesting to have the switch ID or some information that is like consistent between multiple connections. But I believe the only way to do that is if you create another table that is going to store the switch ID. So you can use that information from the table and then encapsulate that information into the digest. So the digest will also contain the switch ID.
Yeah, exactly. This is like a more the manual way of doing things, but you're absolutely correct. And I think we covered in the standard metadata when we were talking about the queue occupancy yesterday, we talked about having this field called switch ID, because in reality you would have multiple switches in a topology, multiple before switches. So yeah, thanks for the observations. Very good questions. How are we doing with time? Let me, Dr. Jorge.
I think we're good, Elite, because this will be the last activity. So yeah, we're good.
Okay, thank you. Let me then proceed. Sorry. Christian, do you have a question? Oh, I see there's a question from Christian. Sorry, I just saw it here. Is digest only used to push data from the data plane to control plane, or is it possible to push data from the control plane to data plane using digest? No, it's more for pushing from the data plane to the control plane. There are ways to do the other way around. So Dr. Jorge was mentioning the packet in out at the beginning of the slides. So this is one way you can do it. Basically, you are pushing a packet. Now, on the other hand, if you want to push some information, for example, that will modify a register field or will clear a counter or whatever, you would do it through the simple switch CLI or the control plane interface, basically. Okay, because remember that the data plane will understand packets. It's not going to understand like arbitrary, bytes unless you program the parser to do
Ellie,
that.
we lost you, or at least I can
Can you hear me now? Yes.
Yes, I can hear you well.
Yeah, I was just saying that you know the data plane will be processing packets basically. If you want to send like arbitrary set of bytes, then you have to make sure to write the parser for that, and this is gonna be super complex if you want to parse like just for specific values that you want to push. So the more you know reasonable way to do it is sending a packet, and that could be using the CPU port you can send out of it. And also there's the concept of packet generation, which is only found in hardware switches. It's not here in BMV2, but essentially you would be able to have the control plane inject a packet that will be sent to the control plane. You can configure timers so that they're executed continuously at like evenly spaced time, or you can do it based on some event. So this is where you would go if you want to push information to push packets to the data plane. All right. And so the other, what we are seeing here is more like explanation of what I said and how we are parsing this in a loop, why we are doing a loop. And then finally, the final thing that we have to do here is in the main function, we want to make sure that we invoke this function listen for digest so that our controller will be listening for these digests. And we have to write in this function listen underscore for digests, and we give it as a parameter here, the controller, or the what is called here runtime API, which is an instance of the simple switch API. So we are passing this controller, and this is gonna be received at the listen for digest. We wait for messages, and then we proceed with the regular scenario that we were discussing before. All right. You're gonna make sure also to save the file. So Control S. I hope that we didn't have a typo. But let's just try for now. So first we're gonna compile the program P4C basic. Okay, so this compiled successfully. We have the basic.json output, which is the data plane specification. And then we're gonna push that file to the file system of the switch. So push to switch the file basic.json and the switch name, which is S1. Password here is password, all small caps, as usual. Now, the other thing that we have to do here is we need to push the control plane to that switch as well. Now, why are we doing that? Well, maybe you want to have this controller controlling multiple switches and having it as a single, you know, software running outside the switch. You can also do that. But for simplicity, we are assuming that this is like a local control plane for the switch. So push to switch controller.py and the switch name, which is S1. I'm just copying this Python program to the switch. Okay. Next, we're going to verify that the files are there. So I will maximize the mini edit and hold the right click on the switch S1 and go to the terminal. And there we're going to issue the ls command to list the content of the current directory. And you can see both files are pushed, the basic.json and the controller.py. Now the next few steps are similar to what we've been doing before, just launching the daemon, right? So simple switch -i. So port 0 will be mapped to interface S1ETH0, and then port 1 will be mapped to interface S1ETH1. And then we have basic, that's the data plane, and then the ampersand so that we run it in the background. All right. Now, another thing we're going to do here in the same terminal is to start the controller. So we're going to invoke here Python controller. And so what you can see, the output that we have here is kind of similar to simple switch CLI, because basically simple switch CLI is doing the same thing that we did in the controller.py. But instead of making it, you know, a batch of or a script that will be executed, it works more in an interactive way. So you push you type in your command and it's going to be executed. All right. Next, so at this point, the tables are empty, right? The maclearn and the forwarding tables are empty. So what we're gonna do, we're gonna send a packet from H1 to H2 so that our switch S1 will learn about the MAC address of H1. And as usual, we go to the terminal, right-click terminal, and there we will send the packet. So send.py 10.00.2 hello world. And back to the switch S1 terminal, let's see what happens here. Well, so you can see that we received something here, right? And if you remember, I'm gonna put, let me scroll, I'll just put the Python code on the side. All right, so basically we received the message and this onMessageReceive was invoked. And then we entered through this loop and we are printing now MAC address. So you can see it here, MAC address. And then we are adding to it the value of that MAC address. In this case, it's 1 because if you look at how the packet was sent from H1, it has the MAC address, all zeros and 1 at the end, right? So here they just compressed it into 1 instead of typing 0000 and so on. And then you have the port. This is the port from which this frame arrives, which is here port 0. So after that, we see that we added an entry for the table maclearn. So the match key is the MAC address, which is 1, right? And the action is no action. So we are basically invoking this line 57 here, right? We do table add, maclearn, no action, and this one. So this was added and we have an entry handle for it. And then we have the forwarding. So you can see here, this is the print message. So for the table forwarding, we execute the action forward with the match key 1. So we are matching on the MAC address 1. If that's the case, we forward the packet out of port 0. Okay, and we can see that it's shown here. And you can see as well that this is still running, right? So it's waiting for further future messages to be received. And this is because of the statement that we have in the controller here, which basically is while true, wait to receive messages. Okay. Now I'm gonna proceed with the next step. So we received this value here. Now we're gonna send a packet from host H2 so that we also learn about host H2. So let's go to mini edit, right click, then get to the terminal of host H2, and then use send.py 10.00.1, some payload. And now back to the switch, we can see that we received now a MAC address, which is 2 from port 1. We added the corresponding entries into the forwarding table. Now, before I proceed, I want to make sure that, or I want to just clarify that we are not really implementing a layer 2 switch in its all functionalities, because basically in a scenario like this, what happens is we don't know maybe the MAC address of H2, then we're going to send an ARP request and the switch will be able to process that and broadcast it out of all the other ports. And then once this ARP is received on H2, H2 will reply back and S1 will learn about H2. So we don't have to manually go to H1 and then H2 and then make them send these messages. But because we are just showing digest here, we had to do them manually. In reality, maybe you want to implement more functionalities like ARP or any basically even custom, if you want, protocols. It's going to be much smoother than what we are doing here. Okay. All right. So now that we populated the tables, what we're going to do is we're going to go to host H2 and then run the receive script such that we can verify that there is connectivity between H1 and H2. Or in other words, we can verify that the tables were forwarded successfully and we can send information between these two end devices. So we'll start the receive.py, which is really just a Python script with Scapy to sniff for packets. And then we're going to go to host H1 and send a packet here. Let's go to host H1. I will use the up arrow to load the previous command. And what we can see is that we received this packet on host H2. This means that in our P4 program, this table forwarding was successfully populated, and we are using the right logic to forward this packet and make it delivered to the receiver, basically. Another way we can verify the correctness of the program is by inspecting the control plane of the switch. And this time I will close the controller.py. So just press in Control-C to kill this Python program. And there I will type in the simple switch CLI to go to the interactive mode of interfacing the runtime of the switch. So simple switch CLI. And as we did yesterday, we can use table dump, and then the table name is in the my ingress block forwarding. And we can see that we have entries here, right? So we have entry 0 here. The match is on the MAC address 1, and the output port is port 0. Another entry is match on the MAC 2, and the output port is port number 1. Right, and same thing we can do for the other table, which is the Mac learn. So I will use the up arrow and just right here Mac learn instead of forwarding. And we can see that also we have these keys, the source address for host 1 and then host 2. Now, basically that's it for this lab, but I just want to also add that we added these entries here, right, in the Mac learn. But if we really want to emulate or kind of write a program that really resembles how a layer 2 switch would work, we have to implement aging as well. So usually you would have Mac learning and aging, in the sense that if those entries are no longer used by the switch, so it's been a while since the table hit on this specific key, in P4, there's the concept of setting a timeout, an idle timeout for an entry. This way, if this entry has not been hit by a certain packet, let's say you configure it for 2 minutes, let's say, then after 2 minutes, automatically this entry will be removed. And this is also like, we don't have the steps here for BMV2, but we tried that with the Tofino switch, the hardware switch, and it works really well. And so in summary, what we did here, we showed how packet digests work, but that was not the only objective of this lab. The other objective was to show how you can create a standalone controller application. And I want to mention that we used here like just the table add. You have plenty of other functions. So all you have to do is just go to Simple Switch API and look what are the available functions there. And you can read registers, right? Do pretty much everything that you have there. And with that, I think we conclude lab number 11. If there's any questions, I'll be happy to answer.
Thank you, Lee. I don't see any question. Certainly, you addressed many questions before regarding this lab. This is the last activity of our workshop. In the chat window, we typed the link, the URL of the survey. We would appreciate if you can take a few minutes to give us your input. This is the first time that we are organizing this P4 workshop. I believe we will do it again, but we want to improve. It's always our intention to improve and keep adding new content. That's in our roadmap. One of the things that we'll be doing is first expanding the libraries. The other thing that we plan to do is do a lab with the Tofino pod, the real hardware. We are doing already. So hopefully by the end of the year, we will have one library with Tofino. But your input is very important. So we will appreciate if you can take a few minutes to complete this survey. And you should also have received an email with the same URL for the survey. A few things, the content, all the PowerPoint slides and the recordings will stay here in this website. So also, I believe that the class in NetLab is for 6 months. Jose, please correct me if that's not right. But
Yes, that's correct.
you will have access to all the material, and if you want to extend, there is no problem. So you will have access to our NetLab system. I don't know if there's anything else. Marian, do you want to add anything before we close the workshop?
No, I think you covered everything. It was very interesting, great to learn new things, and I hope everyone, would love to get feedback from everyone to see how we can learn and improve. Thank you again.
Thank you, Marian. And certainly that's true. We are learning. I mean, we're learning as we do these workshops, and sometimes we don't have all the answers, but that reflects somehow that this is a field that is maturing, is still in development. So again, your input is important. So we will consider and we will address any observation to keep improving these workshops. So with this, if there's no other, one more thing, I believe that the Western Academy issues certificate. So you will be receiving this certificate, I suspect, in the next week. So this is coming from the Western Academy, the co-organizer of this workshop, Western Academy Support and Training Center from California. That will be most likely next week. I will check that with the organizers. Well, with that, we want to conclude this. Thank you, everyone. Have a good rest of the day and weekend. And hopefully we will have you in the next workshop. Thank you.